So this whole entire section is talking about finding the area between curves. If you were given, a shape, a very regular shape on a graph, you could figure out what the area is using all the area formulas yes? Okay. Calculus allows us to find literally any area between our curves, as long as we have our bounds for our x values or our y values, depending on which one it's going to be. So if I drew a quick little sketch off to the side here, what's really happening is, let's say I have a parabola here. Okay. And if I wanted to find the area underneath the curve, we'll call this from A to B, how would I find the area underneath that parabola there? What calculus thing do we use? We use the integral, right? If I integrate my function from A to B, I'm finding all of this area underneath the curve, right? Okay. Now, what if I found, let's say I had another line. Let's say I had a line that looks something like this. Okay, so some sort of line with a slope. And what I actually want to find is this area in between my two curves. Okay, so I know that if I integrate the parabola there from A to B, I'd find that area that's colored in black. But I want to find the area in yellow there. So what would I have to do? Integral of the blue one. So if I integrate my blue one from A to B, we'll just call it f of x. And if I subtract the area of my parabola from A to B, we'll call that just g of x. Okay, then I'm going to end up with my highlighted yellow region, right? Because I take and subtract that big, this would be my blue section, right? All of this, subtract the black line there, and then you're going to be left with your yellow piece. Does that make sense what's happening there? Cool. So that's what we're going to do in this section. We're going to find it both with our x's, and then also talk about when is it going to be smarter to use our y values to integrate instead. Okay. So on your homework, you're going to have questions that most of them you'll be able to do by hand, but some of them you'll have to use a calculator for. It'll say calculator on there, so that way you can practice/remember how to integrate some of this stuff by hand and get practice with simplifying fractions, because I know all of us love fractions. Yes? Okay. So make sure you're practicing that stuff and being careful with your sign usage. Okay. So again, kind of talking or looking at this picture here, on the left side, these are our vertical slices, or we're looking at our x values. Okay, so if I would draw in these lines here, if I slice any of these values here, I touch both the top and the bottom curve, right? So then we're going to integrate with our x values for this curve picture. Whereas on the other side, if I technically sliced vertical again, am I always going to touch both curves here? Or am I sometimes only going to touch one of the curves? If I would draw my vertical lines there. And by curves, I mean this one here and this one here. Would I touch both of those every single time with my vertical slices? No. So instead, we can think about we're going to slice it horizontally. And if I slice horizontally, I touch both curves every single time. But when I slice horizontally, we are going to look at our y values. We're starting down here, we're going all the way up here, right? So to show that distance or that change, we have to say in terms of y is what's changing there. Okay, so do you guys kind of see this difference there between those two pictures of what's happening? Great. Okay, so this first example is going to kind of step us through this one step at a time in order to solve for the area between the two curves. And it's also going to remind us, we got to remember a lot of other stuff when we're talking about calculus. We got to remember how to graph lines and curves and things. And then we've also got to remember how to integrate all this stuff as well. Okay. So Example 1, it says on the grid on the right, to graph the function f of x is equal to negative 1/2 x minus 2 squared plus 6. So what is this shape going to look like? Thinking back to algebra 2. It's a parabola, okay? It's a parabola that is centered at a certain vertex. Centered at what vertex right there? 2, 6. So 2, 6 is my center, or my vertex, sorry. And then with that negative 1/2 out in front, let's go ahead and plug in another value to see what my shape's going to be. How far out are we going to have? So if I plug in 0, or you could plug in 1 if you wanted to, but 0 is easy. If I plug in 0, I get 0 minus 2 is negative 2 squared, which that's going to equal what? 4, and then 4 times a negative 1/2, that's a negative 2, and negative 2 plus 6, that gives me positive 4. So at 0, 4, I have another point, and then parabola is nice and symmetric, so that means I'm going to have another point over on the other side of my vertex at 4, 4. I do remember that kind of shape, same shape there. That's enough points there to get that sketch going of what that's going to look like. So that is my function f of x. Okay, now part B says to find what the value of 0 to 5 of f of x is equal to, okay? And then the next part underneath, it says to shade the region blue. So I'm going to shade it first, actually. So I'm looking at from 0 to 5. I'm finding the area underneath the curve here. Okay, not perfect, but you get the idea, all the way to 5. Okay, so in order to do that, we are going to integrate. Okay, we're given the function, so we can go ahead and just integrate that function. So part B, we are integrating from 0 to 5 of my function f of x, which is negative 1/2 x minus 2 squared plus 6. And then we've got a dx there at the end. Okay, there's a few ways we could do this. We could either FOIL this out first, simplify it, and then integrate, or we could technically let this thing on the inside be my u value, right? And then if this is my u value, if I take the derivative of that, what am I going to get when I take the derivative of the inside there? 1, right? So I'm just going to go ahead and integrate this without FOILing it out, okay? So when I integrate this, I'm going to have my negative 1/2 out in front. And then I've got my x minus 2 raised to the power of 3, or n plus 1, and then divide by 3. What am I going to integrate when I get integration of 6? 6x. Okay, do I need a plus c here? Nope, I can go ahead and just integrate this from 5 and then subtract what I get at 0. So when I plug this in very carefully, again with all of our signs, I'm going to have a negative 5 minus 2, which is 3 cubed, divided by, this would be 2 times 3, which is 6, not 5. And then plug in 5 to the next thing. I've got plus 6 times 5, which is 30. So that's my first piece, plugging in 5. And then I'm subtracting what I get when I plug in 0. So if I plug in 0, I end up getting a negative 2 cubed over 6. And then 6 times 0, that's just 0, right? So I've got this stuff in parentheses there. Again, we're doing this by hand. We're going to answer in terms of fraction here. So I've got my negative 3 cubed. That would be negative 27 over 6 plus 30. Now we got like 3 negatives going on here in this next piece. So negative 2 cubed. This piece would give me negative 8. But then I've got a negative 8. So positive, right? and then I've got a minus out in front. So it's actually going to be minus 8 over 6. All agree so far? Okay. And then let's go ahead and make common denominators here. So let's multiply this 30 times 6 divided by 6 on that one. And when I do that, I'm going to have negative 27 plus 180 minus 8. And that's all divided by 6. And then if I simplify that on the top carefully, that's going to equal 145 divided by 6. Okay, any questions on how I got that? Cool. All right, so that was part B. Part C we already shaded. Part D says to graph the function g of x is equal to 4 minus 1/2 x. What is that going to look like? 4 minus 1/2 x. I heard someone say it's a line, right? And it's a line that's going to start at 0, 4. So we're starting at 0, 4. That negative 1/2 is a slope, so go down 1 over 2, down 1 over 2. And then part E is asking us to integrate that value and to shade it green. So if we're integrating again from 0 to 5, I'm taking and I am finding all of that area there in green. So part D, if we integrate this from 0 to 5, 4 minus 1/2 x dx. Integrate each of these individually, and then we can evaluate it at 5 and 0. What am I going to get when I integrate 4? 4x. And then when I integrate negative 1/2 x, that would be negative 1 over 2, but then times x squared over 2. Yes? And this is going to be evaluated both at 5 and at 0. So I could go ahead and plug in 5, plug in 0. So I'm going to end up getting 20 minus, then 5 squared, so 25 divided by 4. And then if I plug in 0, I end up getting 0, right? So minus, technically you're minusing 0, but that's not equal to anything. And then I can simplify this 20 minus 25 over 4. Let's maybe multiply by 4. Top and bottom there. So I'd end up with 80 minus 25 over 4, which, simplify that carefully, subtract, you should get 55 over 4. Okay, last piece there says, how would you find the area of the region that lies between the two graphs? We talked about this once already because B is this entire blue region. Part D was just this green region. So if I want to find out this region here in red, what would I need to do? Subtract them, right? So part G, we would subtract my g of x area from my f of x area. Or think that's my green area, and this is my blue area that I had. Technically, that would look like, let's see, 145 over 6 minus 55 over 4. We could simplify that. We could make it common denominators, but we're just going to leave it like that for our answer right now, okay? All right, so again, our general approach now, instead of having to find the area of each one separately and then subtracting, there's a formula that you can use in order to subtract and find the area of those curves, right? So if we were to look at this formula here, Do we not agree that this would be the same thing as the integral of 0 to 5 of f of x, and then minus the integral of 0 to 5 of g of x dx, right? Isn't that the same thing? Where what we just set up above in the previous problem, we said that we're going to take this g of x area and subtract it from this f of x function. So it's just another way of writing the exact same problem. So we're going to solve the problem again, but solving it a little differently this time. And then it's a little bit shorter. You do more of the algebra at the beginning instead of at the end, okay? So if I plug in my f of x function and my g of x function, I'm evaluating from 0 to 5 of, let's do my negative 1/2 x minus 2 squared plus 6. So that's my f of x function. And then I'm subtracting my g of x function. So subtracting 4 minus 1/2 x dx. And now before I try and integrate any of these things individually, let's just do a little bit of algebra to make this look a little bit nicer so that way we don't have to integrate all of that stuff, okay? So, careful with your algebra here, parentheses first, right? You gotta factor your stuff out here. So I'm gonna go ahead first and distribute this x minus 2 squared. So that's gonna give me negative 1/2 times x squared minus 4x plus 4 plus 6. And I could distribute that negative, so I get minus 4 plus 1/2 x. And this is still all in my integral. So now I can distribute, and then I can simplify, combine my like terms. So I've got from 0 to 5 of negative x squared over 2 plus 2x minus 2 plus 6, and then minus 4 plus 1/2 x. Don't you love algebra? It's just so fun. Okay, what happens with this negative 2 plus 6 minus 4? What's that going to equal? 0, so that goes away. And then if I combine my like terms, combine my x's, combine my x squared, so if I got them. So from 0 to 5 of negative x squared over 2 plus 2x plus 1/2 x, so that would be plus 5x over 2 dx. Okay, so now instead of integrating two separate pieces, yes, we had to do a little bit of algebra first, but instead of integrating two separate pieces, we can just integrate this function, evaluate it at 5 and at 0, and then we'll end up getting the same answer, okay? So if I evaluate this, I get negative x cubed over, this would be 2 times 3, which is 6, right? And then if I integrate 5x over 2, that would be 5x squared over what? 4. And I'm evaluating this both at 5 and at 0. When I plug in 5, I end up getting negative 125 divided by 6. And then plus 5 times 25. 5 times 25 is what? 125 again. So 125 over 4. Okay, so our answer looks a little bit different than what we had up above, but if you combine this, simplify it common denominators and add those together, it should end up being the same thing. It's just a different way of solving it, okay? This is how we are going to be solving these problems. Instead of setting up separately, it'll just save us some time when we're doing it, okay? Questions on that? Okay. This next one here. Okay, so this previous one that we did, we were able to look at the x values. Okay, if I look at this example, there are 2 ways that we can do it, okay? if you look at this, I've got x equals 3 minus y squared. So that is going to be what? My sideways parabola or my straight line? My sideways parabola. And then I've got x equals y plus 1. That's going to be my straight line. Okay? Also, another thing to notice is that sometimes on the homework or sometimes when you're solving these problems, you might not have an answer in terms of x equals or y equals. It might be like x plus y equals this or x plus y equals this. You're going to have to solve for one of your variables in order to graph it, okay, and in order to do your integration stuff. So this WRT right here, this stands for with respect to, and then it says with respect to x. So we need two integrals with respect to x, but if we do with respect to y, we only need one integral. Okay, and I'll explain why that is here. So if I'm looking for the area in between this curve, so I'm technically looking for, I'll color it here in yellow, I'm looking for this yellow area, right? If I were to slice this vertically, do I touch both curves every single time, all the way to the end? No, I touch it almost up to I touch it to 2, right? So that's where it says from -1 to 2. We could do the integration from -1 to 2 of my x values. That would be fine. And from 2 to 3, I would have to do a separate integration for that curve. Okay, or instead of doing that, it'll make our lives a lot easier if we were to instead, let's look at this horizontally. If I look at this horizontally and I slice all of these pieces and I find the area between these curves here, do I touch both curves every single time? Yes, okay. Remember this curve right here, that's your 3 minus y squared curve. And then this one is your y plus 1 curve. Okay, now why did they use from -2 to 1? The previous one was -1 to 2 and then 2 to 3. So why did they go from -2 to 1?
That's where they intersect on the y-axis.
It's where they intersect on the y-axis, -2 and 1. Wait, do you mean like where they intersect the points right there? Not like on the y-axis? Yeah, that's exactly right. So if we look at these points right here, right, it's specifically my y values at those points because this is -1, 2, and this point is at 2, 1, right? So if we're integrating now with respect to y, that means my integration variable or my bounds have to change as well. So I'm going from 2, or sorry, that's -2. I just can't write. That's a -2 to +1. Okay, so think about like if you're looking at it on the side, right? You're starting down at your lowest point and going up to your highest point, okay? But when we're integrating this, you always start with the top curve and subtract the bottom curve, okay? So in this case, my top curve is the 3 minus y squared, and my bottom curve there is the y plus 1 because I'm looking at it horizontally, okay? So we're going to integrate this with respect to y, so from -2 to 1 of my blue function minus my red function. So 3 minus y squared, and then I'm subtracting my y plus 1. Okay, other thing that you should note here is that I only have one variable, right? I've got y, and a dy. If I was using x, I should only have something in terms of x, right? Same thing, my bounds here are in terms of y because I'm given a function in terms of y, okay? So let's do a little bit of algebra here, simplify it, and then we can integrate it. So if I integrate this, -2 to 1, this would be 3 minus y squared minus y minus 1. Simplify it one more time. Combine those like terms, 3 -1, that would give me 2. So I've got -y squared minus y plus 2 dy. Okay, I'm going to give you a minute right now. I want you guys to go ahead and integrate this and evaluate it both at 1 and -2 and see if you get the same answer as me, which should be 27 over 6 after you go through all of the being very careful, simplifying common denominators and all that stuff. Okay, so I'll give you a few minutes to try that out, and then I'll show my work up here quick as well to make sure we're all on the same page. The rest of this simplifying stuff can be done by making common denominators here, so I'm going to make them into 6. That's how my brain works. And then this becomes minus positive 8 over 3, which is actually 16 over 6. And then negative 6 is a positive 6 or a positive 36 over 6. And if I add all those numbers up on top together, I end up getting my 27 over 6 or 9 over 2 or 4.5. All of those answers would be fine. Okay? Okay, so like I said, on your homework, you're going to have multiple questions that say calculator, and you'll have questions that don't say calculator. So don't use your calculator unless it says to use the calculator, okay? Because there will be a non-calculator and a calculator portion on your test that you'll have to be able to do these integrals by hand on, okay? So example 4 says to find the area between the graphs of f of x and g of x. So if I look at these two graphs, they're already graphed on our function over here. So g of x, which one is g of x? My 2 curves or 1 curve?
1 curve.
1 curve. This piece right here. My f of x, then that means is my other curve. Okay? So it says to find the intersection of the 2 curves. So what we're trying to find is this area between my curve here and the area between my curve there. So I have 2 different pieces that I'm going to have to find the area of to add them together. Okay? But in order to do that, we aren't given actually what these values are, so I need to find out what these values are. How could I figure out what those x values are if we're looking at curves where they cross? How do we do that algebraically? Set them equal to each other, right? If I set them equal to each other, doesn't that mean that those values are going to be the same, so those points would be the same, right? So if I not cross multiply, but set 14x plus x squared minus 2x cubed equal to x squared minus 4x, I will be able to solve for all 3 of those intersection points, okay? So I'm going to get all my x's onto one side. Nicely, these x squareds go away. So that's cool. I'm going to move everything over to the right side so they're positive. So I've got 0 is equal to 2x cubed plus 18x. We got a little algebra we can do here. What can I take out? 2x. So take out a 2x. And I get x squared plus 9. Wait a second. Yeah. X squared plus 9. Wait. Yeah, I do have a mistake there. What's my mistake? It should be negative. I was going to say, otherwise this isn't going to work out. So this should be a negative 18, which makes this a negative 9. Okay, there we go. Now we're working. Okay, so now that I've got this, I can go ahead and use my zero product property, set 2x equal to 0, and solve where I get x equals 0. And then if I set x squared minus 9 equal to 0, what are my 2 answers going to be there? Plus or minus 3, right? So all of these intersection points over here, this one is obviously going to be at negative 3 and crosses very nicely there at 20. This one right here crosses at 0, 0. And then this one right there is a little harder to see where it crosses, but it's at the x value of 3. How can I figure out the y value? Plug it into either function, right? So if I plug it into my g of x function, 3 squared minus 4 times 3, that gives me negative 3, okay? But when I'm actually integrating this, let's think about, do I want to make vertical slices and use my x values, or do I want to make horizontal slices and use my y values? Well, if I look at my vertical slices here, am I always going to touch both curves no matter where I'm at? Yeah. If I would go horizontally, would I touch both curves every single time? No. So we are going to do vertical slices, which means we are going to use my x values when I'm integrating this, okay? But we are going to have to integrate 2 separate times from this -3 to 0, and then again from 0 to 3. The reason for that is because my top curve here is my red curve, my bottom curve is the blue one, but then it switches in my next case. My next case is starting with my blue curve on top, and it ends with my bottom curve as red, okay? So we're going to have 2 separate integrals that we're going to solve to find the area of those 2 yellow pieces, and we'll add them together, okay? So area 1, let's do area 1 first. So we'll call this area 1. So we're going to integrate for my x values from -3 to 0. And then when I'm setting up my formula, I'm taking the top curve minus the bottom curve. So it's going to be g of x minus my f of x function. Okay, so that's the order of how we're going to integrate that. And if I do g of x minus f of x, so I'm taking this g of x function up here, and I'm going to subtract my f of x function, subtract the entire quantity, I'm going to end up with, let's see, x squared minus x squared, that goes away, right? And then I've got a -4x minus 14x, which would be -18x. So those are gone, and then I've got 0 minus a -2x to the third, so that's going to be plus 2x to the third. Okay. Okay with that subtraction there? Okay, and then we can go ahead and integrate this. When I integrate -18x, what am I going to end up with? -18x squared divided by 2. And then the next one would be 2x to the what? 4th divided by 4, okay? And I'm going to evaluate this at 0 and at -3, but I'm going to simplify it one quick time here. So this is actually -9x squared plus x to the 4th over 2. And I'm evaluating it at 0 and at -3. Okay, so plug in those values here. We end up getting 0 minus, plug in -3, so that's -9 times 9. And then what's -3 to the 4th power? +81, yeah. So that would be plus 81 over 2. Okay, 9 times 9, that's -81. And then 81 over 2, that's like 40.5, yeah? So if I take -81 plus 40.5, I end up getting -40.5, but then there's a negative in front of it, so it's actually 40.5. Okay. So my first area right here is 40.5. Now the only thing that's going to change from my area 1 curve to my area 2 curve is what? The bounds and also the order, right? So I guess there's actually 2 things. So instead of taking my top curve, which is the red one here, and subtracting my blue curve, my top curve in my second section is blue, and then we're going to subtract the red curve, okay? So for area 2, we are doing the integral from, well, what are my x values we're going from? We're starting at 0, and we're going all the way over to what? 3. So I'm going from 0 to 3 of my top, which is f of x, which is the blue function. So f of x minus my g of x function. So if I take my f of x function and I subtract g of x, so subtract x squared minus 4x, let's see, those x squareds go away again. And then what am I going to end up with when I combine these? Careful with the negative. 14 minus a negative 18x, and then minus 2x cubed, right? Which is almost identical to what we had except for different signs, right? So we're integrating from 0 to 3 of 18x minus 2x cubed dx. Which we literally already integrated over here, right? Except for the only difference. What's the only difference going to be for my integration that I get? Yeah, the signs are going to flip, right? These are the exact same thing except they've got different signs. So we're going to flip the signs here. So this is going to become, let's see, positive 9x squared minus x to the 4th over 2, evaluated at 3 and at 0. So I plug in 3, 9 times 3 squared. That's going to give me 81. And then 3 to the 4th, 81 again, divided by 2. Subtract those together, I also end up with 40.5. So both of those areas do just, in fact, end up being the exact same thing. That's not always going to be the case. But then what does that mean that my total area is going to be?
81.
Yes, 81. 81 total units squared. Add those together. Okay. Oh, also, I meant to say on this last one here, on your calculator, do you guys all remember how to find the intersection points on your calculator? Because you can do that obviously with a calculator quicker than doing it by hand here. But again, calculator versus non-calculator question, right? You'd be able to solve one like this without a calculator. There might be ones that you have to evaluate with a calculator and integrate on your calculator instead, okay? This one is not that case. This one we can, again, do by hand. It's asking us to find the area of one of the regions that's bounded by the sine and cosine curve. First thing we got to remember is which one's which. Sine starts where? At 0, 0 or at 0, 1? 0, 0. Very good. All your all your pre-calc teachers are proud. Okay, so sine is this one, which means cosine is my other one. Okay. Now I've technically got two different areas that are enclosed here, right? I've technically got this area for this graph, or in between those two x values, and I also have this area over here that I could find. They're both going to be the exact same thing. Do we agree with that? Yeah. So we only need to find one of them because it just says to find one of the regions bounded by sine and cosine. Now it depends which one we want to do. If you look at this notation over here, it says that we want to identify what f of x is and g of x is, but f of x is bigger than g of x. So if I'm looking at this first interval here, my blue function is bigger than my red function, right? So my sine function is bigger than my cosine function in the first interval. However, what changes in the second interval there? Which one's bigger in the second interval? Cosine is bigger here, and sine is your smaller one. Okay, it just depends on which section you're in. So I'm just going to go ahead and go with the first section, but again, either way you find it, it should give you the same area. So what I need to do is I need to find out what is this x, not this value, this x value here, because that's where it starts, and then this is where it ends. So where's that intersection point? Okay, so we're looking at where is sine and cosine equal to each other. It's nice because they gave us a graph. So if you look at this graph and use the scale, we could figure it out pretty easily. Or you can think about your unit circle. Where are your sine and cosine values the same at? There's 2 points. What 2 points are those? Where's sine and cosine going to be the same? Pi over 4 and 3 pi over 4, you're close, but one of them's negative, one of them's positive. It's going to be at 5 pi over 4. Okay, I'll draw a little unit circle off to the side here. So remember, here's my unit circle. So this point right here, that's my pi over 4, which is square root of 2 over 2, square root of 2 over 2. And then this point, 5 pi over 4, same thing except for it's negative, right? Make sense? Okay. So again, we're going to take the area of the top curve minus the area of my bottom curve from those two x values and then evaluate it, and that's your answer of the area between the two curves. So my bounds, what we just found, those are your pi over 4 to 5 pi over 4. So when we are integrating it, because we're using this first section here, I'll call it A1, my setup would look like this. From pi over 4 to 5 pi over 4 of my top curve, which is sine of x, minus my bottom curve, which is cosine of x. Okay, so if I integrate this, plug those values in, I will get my answer. So we need to integrate first, which means we got to remember our trig integrals. When I integrate sine of x, what am I going to end up with? Negative cosine. So I'm going to have negative cosine of x. And then if I integrate cosine, I end up getting sine. So I'm going to have minus sine of x. And I'm evaluating this both at 5 pi over 4 and pi over 4. Okay, so I'm going to plug these in. Negative cosine of 5 pi over 4 minus sine of 5 pi over 4. So if I look over at my unit circle, 5 pi over 4 is this coordinate point, okay? So cosine and sine of that value, those are both going to be what?
Negative.
Negative. So a negative, negative, which makes it a positive. So this is just square root of 2 over 2 plus the square root of 2 over 2. Okay, but then we're going to subtract the entire quantity. So that's where people mess up here is we forget our parentheses. We're subtracting the entire quantity of what we get when we plug in pi over 4. So negative cosine of pi over 4 minus sine of pi over 4. Okay, so if I look at my pi over 4 coordinates, those are both positive. So I'm going to have minus a positive, or sorry, no, actually, it's positive, but there's a negative in front, right? So it's negative square root of 2 over 2, and then minus square root of 2 over 2. Good so far? Careful with all those negatives. If I'm subtracting both of these, that's the same thing. If I distribute that, it's adding all of them. So I've got square root of 2 over 2 plus square root of 2 over 2 plus a square root of 2 over 2 plus another square root of 2 over 2, which means how many square roots of 2 do I have? 4. So 4 square root of 2 over 2, which equals 2 square root of 2.